Hello, hello. I wanted to record one of my introductory lectures. I never really had a chance to do so, and I thought this might be a good thing. I had one recorded a little while back, a few months back, but then things got very busy. And so now today I'd like to kind of go back to that. And the question I'd like to explore today is where does magma come from? And let me see if I can share the screen easily now. So, share. So I think you can see that now, and I can go on projection mode as well. It might be nicer. So I hope that works. So I'd like to start here with this image of the interior of the Earth by Athanasius Kircher. This goes back to the 1670s, I think. And he had the idea that there were certain cycles. There's a water cycle and there's a fire cycle. And the fire cycle would then bring a material to the surface of the Earth. You can see a little volcano here. Later, he, was questioned. Other people believed that basalt would actually form from precipitation of ocean water, and it would form in this realm here, would be part of the water cycle rather than of the fire cycle. And then he got, forgotten for a little while, but now I think we're back to the fire cycle. We understand that magma is forming from melting of material inside the earth, and then it travels to the surface and erupts in a hot state. We've seen it at many volcanoes. And in the 1920s and 30s, it was down to Norman Bowen to suggest how the process of magma generation and magma differentiation actually works. So he suggested that parental magmas, parental volcanic rocks that we see that have given rise to entire series of magmas, they are basaltic in nature or gabbroic in a plutonic form, and they form from melting of ultramafic rock in the mantle. And the mantle is dominantly made of peridotite, at least that's our understanding. There was a discussion in the 60s about eclogite being a major component of the mantle, but that's been discarded. And that's a different discussion. But the peridotite that we understand to be the dominant rock in the mantle is essentially made of olivine, clinopyroxene, and orthopyroxene. And if you heat that combination in a rock up, then you are producing a basaltic melt. But an important issue here is the degree of melting. If you melt it just by 1 or 2% or by 10 or 20%. But we'll come to this in a few minutes. So 40 years later, this whole concept became testable, and their partial melting experiments have been conducted in many forms now. And here is the concept. We have a fertile garnet leusolite is a type of peridotite, and this comes from Lac de Leurs in France. And the garnet component has a lot of aluminium, and if we start melting that, we're extracting a basaltic magma, but we're also producing a restite that's still staying behind. Usually that's with the olivine component, because that's the hardest to melt. Olivine has the highest melting point, and there may be some pyroxene staying behind as well. If we look at the diagram on the left here, then the mantle is the source of this melting process where basaltic magma is produced. This magma can then segregate, rises up, and usually collects, often at the base of the crust, at the moho, and there it might differentiate, and then some residual liquid, some evolved liquid might rise up further and eventually get stored again to evolve even further, or it might actually yield an eruption at the surface. But it's only a fraction of material that erupts at the surface from the magma that's produced at depth. So Bowen, he was quite a person with foresight. He predicted already on the basis of his experiments that when mantle rock begins to melt by decompression, then a minimum melt fraction will form, a small degree of melt, and this will segregate in small little pockets, and it leaves behind a residue of non-melted, but in this case, then depleted minerals. The collected liquid is compositionally different to the mantle rock, but it will be in equilibrium with the mantle under certain PT conditions. That means it will contain the same chemical components, but in different proportions. Once the liquid moves away from the source, pressure and temperature will change, and then the face assemblage will change as well. And that's when the magma starts its own life independent of the source. So, depending on the degree of melting, the initial melt can be very enriched in certain components. For example, lithophile elements, alkali elements, for instance, they don't like to stay in the melt, in the residue. They like to stay in the melt because they're large iron lithophile elements. So they will preferentially enter the melt. And that means very small fractions of melt have a somewhat different chemistry to larger fractions of melt. And there's essentially three ways of achieving melting. And here we have a simple diagram. The red line is the geotherm. That's the temperature increase when you go into the earth. And then on the right hand, we have peridotite and melt and the dry melting curve, the white dotted line. So the two don't actually cut each other, they don't overlap. So the geotherm and the melting of a dry peridotite, well, it's very challenging. So here we need to do things to it. And the option that is given here is A, this one here. That is when we increase the temperature. We need to heat up the mantle somewhat, then we can get it to melt. And that's what we think happens in hot spots and heat anomalies. The other option is we lower the pressure, we rise the mantle rock, and once it is rising at a certain temperature, but with reduced pressure, and then it enters this field of peridotite melting. Or the last option here is we can actually lower the melting point by adding another component. So if we add, for example, water here, then we have a wet curve, and the wet curve, the red one here, will also kind of allow the mantle to melt. Having mentioned the decompression, I should add that this is what we actually see when plates are rifting, when plates are spreading, there's decompression. Material can rise up and can then melt. So when we look at this, this is pretty much how we picture this in situations where we have a hotspot melting is achieved by additional heat and of course also by upwards movement, so it's a combination of A and B. Then in subduction zones we are adding water from the downgoing slab, and that changes the mantle wedge chemistry by percolating fluids, and that would allow melting. And then of course at mid-ocean ridges, for instance, we have a rift system, and that rifting, often by pulling the plates at the subduction end, will allow material to rise up and melt. And this is option B, and that would be typical for mid-ocean ridges. So, and then here on the right hand, there's another option, and that's supposed to be also a plume type hotspot system, but in the ocean, and that would be Hawaii or the Canary Islands, for example. So you can change the temperature, you can change the pressure, and you can change the chemistry. These are the three options to create melting in the mantle. When we look at the minerals a little more, here is our beautiful diagram from Hans Schminke's textbook on the right-hand side, and there is a little classification diagram that goes back to Mr. Streckeisen. There we can work out most of the mantle peridotites. They have olivine, CPX, and OPX, and if they fall into this area here with more than 40% olivine, then they're called the leursolites. That's the most common type. There is a few other types here, a Harzburgite after the Harz Mountains in Germany. They are actually formed when you remove the CPX component. And here's a Wurlite after a place in the Eifel volcanic region, also in Germany. There we have no OPX, but CPX and olivine. So these would be peridotites, and these would be more like pyroxenites. And here the obvious issue is if we start somewhere in the leusolite field, then say here, and we're removing the OPX component, we're taking this out, then obviously the residue that will stay behind will also change its composition. The residue will actually be more of a Harzburgite then. By taking the CPX component, simulating our magma that we are producing, we can then increase the melting degree. And if we take the OPX out as well, so if we take the OPX, then the residual rock will be pushed more and more towards a dunite composition. And dunite comes from the Dun Mountains in New Zealand. This is a very olivine-rich rock where olivine forms more than 90% of the rock. So if we look at the same problem here in a tabulated form, then we can increase the melt fraction and extract it. So if we start with an leucellite, which has olivine 60-70%, it has OPX and CPX, and it has an aluminium compound often present as garnet or at lower pressures as plagioclase, or at intermediate pressures as spinel. And if we take a component out of that, we will increase the olivine, but we will decrease the CPX and the aluminium component. And if we increase the melting, we will eventually also take out the enstatite, the OPX component, and the CPX component entirely, and likely most of the aluminium compound. And we're left with a rock that is effectively olivine plus a few bits and bobs. So by taking out these components, we are creating a dunite, and that means we have actually melted the mantle rock to a high degree. So this was looking at the residual fraction, but let's look at the melt a little more. So this is when you dissolve the minerals and you leave the glass behind. This is from a mantle peridotite, this particular image. And there we see a melt network. And this was an olivine crystal. This was another olivine, and this maybe a pyroxene. And it's been shown now that this is how melting works. It melts at the grain boundaries, and then it spreads out, making a network of melt. And if there's a lot of pressure, this melt, once it's connected, can respond to it. It can escape upwards, for example. And if it was isolated pockets, then even if you squeeze it very hard, it wouldn't do very much, even if the melt fraction is reasonably high. But what we see is that actually the melt spreads along the grain boundaries. This is an inherent feature of the system, and this will always happen in these type of rocks. So therefore, the melt films that we are getting connect, and they make a network. So there's a crucial observation, and this means that when we have these triple junctions where three minerals meet, that's where the melt likely starts to form, and then it creeps out and connects with other little triple junctions. So sorry, the quality of this diagram is a little poor, but when we change the degree of melting, I hinted at that earlier, we actually change, in particularly the alkali element content. Alkali elements like sodium and potassium are large, low charge elements, and they are happier, so to speak, in the melt. They're more likely to be in the melt once we're starting to actually break down a mantle rock, and the more compatible elements stay behind, those with higher charge and lower radius. And there we will see systematic differences as a consequence. So the higher the degree of melt, the more olivine rich is the residual rock. That's one thing, because we're taking out the other mineral components. But it also means that the higher the degree of melting, the less the influence of the alkali elements, because they get diluted. So the initial melt, very small degree of melts, will have very high alkali content. They may even be nepheline basanites, very alkali rich. Nepheline is a sodium mineral. And then if we increase the degree of melting, we still may have a leucellite as a residual one, here leucellite, but we have an alkali olivine basalt. That's a typical rock that forms, or lava that forms on Hawaii, on the Canaries, and Iceland. We sometimes have it as well. But if we go to higher degrees of melting, we then get to Harzburgite. That's when we have taken CPX component out almost completely from our mantle rock, and we actually get a tholeite magma. And that is more evolved. It's a little higher in silica as well, and it's much lower in alkalis, because now the degree of melting doesn't concentrate these alkalis in the initial stages, in the first drops of melt. And if we melt really high and break down the framework of olivine that's left in the source, we get a pickrite. Pickrite is a basalt with high proportion of magnesium and high proportion of olivine usually. And what we are left behind is merely olivine. So this is kind of how this works. And in the TAS diagram, this would look like that. The TAS is the total alkali silica diagram that we use to classify rocks. So usually basaltic rocks are on the left. And if we start off with a basaltic rock and we let this fractionate, then we are extracting certain components. We are going into the maybe trachyandesite and rhyolite stage. This would be a normal evolution, and this would be a basalt which has a pretty high degree of partial melting. And this is the evolutionary direction. However, if we change the degree of partial melting, it doesn't affect the trends going to the right because that happens after the source has formed or after the magma has left the source. The important thing we want to discuss today is the decrease of partial melting. And if we, as we said, decrease the degree of partial melting, we're increasing the alkalinity. So if we are over here with higher alkali content and lower silica content in a smaller degree partial melt from the mantle, we will also get trends going to the right, but we will get them in slightly different places. So here in the turquoise and in the red trends, let me show that in this one here and this one here, we're starting with a more alkali parental magma, and we then have the trends of differentiation to the right. And if we are here with a nephelinite, we can have a phonolytic nephelinite and a phonolite at the end, while here in a more sub alkaline suite, in a more normal kind of mid-ocean ridge type suite, we would actually go from a basalt to an andesite or a trachyandesite, and then to a rhyolite. Now, this is exemplified in many of these task diagrams that we often see. This is from the Scottish provinces, and this looks at the Skye main lava series and the Mull lava series. These are two tertiary volcanoes with a large lava field or with large lava fields surrounding them. And there we see that there's some variation down here, and that's the source variation. And the more it's pushed towards the upper left here, the lower the degree of partial melting. And the further we go down here into the basalt field, the higher the degree of partial melting. And the tholite magmas here have the highest degree of melting, therefore, while the more alkali earlier magmas, they sit a little bit more over there. So this is very interesting to observe. And now I'd like to quickly run through the different tectonic provinces we have on Earth and give a little summary just to cement this discussion a little more. So magma series and igneous provinces, the principal locations of magma production are plate margins, and that's where most of the magma is produced, but also within plates, and we'll come to this. But let's start where most volcanoes are actually located, and that is at mid-ocean ridges. In fact, 85% of all volcanic rock is produced at mid-ocean ridges, and that's also where we make oceanic crust. How do we produce magma there? Well, it's by decompression. We are partially melting the upper mantle rock because we're moving plates apart, and that allows it to well up, and that decompression allows it to melt. It only allows it to melt to a certain degree, but it's a pretty high degree. And here we produce tholiites. It can be up to 30% of the mantle rock that's actually melted here. And this is clearly a subalkali rocks. There is a huge dilution effect. Also, the upper mantle has usually produced magmas in the past because ocean crust has been produced for a long, long time. So often the source doesn't have a lot of alkali elements to start with. And that is a typical feature. It makes mid-ocean ridge basalts very depleted in some of these large iron lithophile elements, not just alkali, but also other trace elements. But that's another kind of topic. Now, when we look at these kind of systems, we also want to, obviously, as geologists, get our finger on it, and we can study them, of course, by looking at submarine systems, but that's often a little hard to kind of get there. So you want to look at abducted pieces of ocean crust, and we have that, of course, in ophiolites. So, and here we can then come up with a structure from the few drill systems and seismic investigations that we have, plus the knowledge from ophiolite. And there we know that there's an intrusion at several kilometers depth, and this can actually be kind of cigar-shaped, this intrusion, and it is often below the axial ridge. And when we kind of pull the ridge apart, then new magma is coming in, and of course sometimes it also erupts. Only the very top of this intrusive system is believed to be liquid. This is probably a mush system, and the mush gives rise to the gabbros of the ocean crust. So here we have two cuts. One is parallel to the ridge, and this one here is perpendicular to the ridge. So here we have the crystal mush and a melt lens on top. And this material, the crystal mush, will eventually give rise to the gabbros when we put magma in and spread it. Then more and more of this mushy material will be pushed aside. So, and periodically we have a little bit of an eruption from the liquid melt lens and the channels that allow this magma to rise up to become lava. That is actually what makes the dikes, the sheeted dikes. And of course, when material then erupts on the ocean floor, we have pillow lavas. Well, that's the Leidenfrost effect here. We have an insulating film of steam between the hot lava and the ocean water, and that then also allows to form a crust. And then there is still magma movement or lava movement inside these tubes, but well, they are initially kind of reacting maybe with a little steam explosion, but once the magma or lava is traveling just inside these tubes, then there is usually no such effects. Then the other thing is often when they're cut perpendicular to flow direction, they look like pillows, but in reality, they're more like tubes here. So they're effectively little lava tubes. And here, as an example, here's the mid-ocean ridge system that goes all the way from the North Atlantic to the South Atlantic. And here it moves into another ridge system. And we have magmatism all along this system. As I said, 85% of the Earth volcanic rocks are produced at mid-ocean ridges. We know this, of course, from actually some expeditions down there, and submersibles have been helping us here. We also know that there's a lot of these black smokers, these mineral-rich vents, and this is when we have hot water seeping into the crust and then getting close to the heat source, and then it leaches out certain materials. And when the hot, acidic, um, mineral-laden material comes out and hits the cold seawater, this hot water will actually start to lose its materials. It will start to lose its carrying capacity, and we have a lot of tiny little needles of usually ore minerals forming, and they can be rich in copper, iron, zinc, etc. So there is a lot of mineral wealth down there in many of those places as well. So, and here coming back to the TAS diagram, the tholeiitic series at mid-ocean ridges, it's placed roughly here in the lower part of this diagram. And indeed, many authors use a dividing line between subalkaline and alkaline systems. And this tholeiitic system should fall pretty much on or below the subalkaline-alkaline divide. So a few words about ocean crust. Large parts here are actually solidifying as gabbro, as I said, and then the material, the magma that moves up can actually, via these dikes that become sheeted dikes, then erupt at the surface, making surface of the ocean, that is, the bottom of the ocean, and making some lava pillows there. And this sequence is actually very characteristic. We see this also in the ophiolites, as I said, and this is the layering of the ocean crust. So I'll repeat that here. We have mantle rocks, and then very often there is a cumulate area here, and then we have gabbros, a dike swarm, and then we have the pillows, and often also sediment that becomes increasingly interlayered with the pillows on top. So this is the typical profile of the ocean crust, and it's generally about 6-7 kilometers thick, and it doesn't get a lot thicker simply because we can't melt a lot more of the upper mantle rock that is not particularly fertile. So that's the limit to that. A few words about subduction now, and that is where ocean plates that have gotten old will sink back into the mantle or where they're forced underneath continents, and that's often resulting in continental or island arc systems. And here are some examples: the Ring of Fire all around the Pacific, but there is some subduction also, of course, in Europe, in Italy, for instance. And these tend to be more explosive in nature, these kind of rocks, because, as we said earlier, there is usually more water in the system because of the subducting slab bringing in extra fluids, and they will, of course, make the system a little bit more explosive. Now, how do we know that subduction occurs? Well, we know it from seismics, for example. So this is a trench in Central America, and there we can see the cold slab being subducted and being subducted almost all the way down to the core mantle boundary at 2,900 kilometers depth. And there's a few cold areas here. Some people refer to this as the lithosphere graveyard. This may be formerly subducted materials that are residual and they're hanging out down there until maybe recycled by a plume or something of this nature. So here we have some subduction systems marked, and they're usually those red areas here. That's the Indonesian arc, the Sunda arc, and here we have the Andes, and here the Cascades up here. The Andes are more clearly defined on this projection here. But in principle, it looks like this. We have a slab that's going down. If there's two oceanic crusts, it's the older slab, the denser one that goes down. If there is an oceanic crust that meets a continent, well, the continent is made of granitic rocks, broadly speaking, that makes it lighter. So the ocean crust being made of basaltic rocks is denser, and then it will be subducted under the continental area. That would be typical for the Andes, while the ocean situation is maybe more typical for other subduction zones, like the ones in Indonesia, for instance. So, and here we have these two examples, an ocean system, and here an ocean continent system. And here's a prime example. This is Mount Rainier in the Cascades in the northwestern US. And it's a classic stratovolcano in a subduction system. And it sits close to Seattle, as we all know. And of course, there's a potential risk for the volcano erupting or collapsing. So often subduction zone volcanoes, strangely enough, they are very attractive. And this is the same in Indonesia. We have a lot of people living around some of these volcanoes. Not all of them, of course, but yeah, they have a beautiful microclimate. The soil tends to be very fertile because of the ash eruptions that have been going on for a long time. So these areas are generally attractive. And here is a photo of Mount Rainier in a snow cover, and this is how it looks from a little distance. Now, how would it erupt? Well, likely it would erupt like Mount St. Helens in 1980, which is the image here on the right. This was instrumental for us to understand subduction type volcanoes. And what really happened is that the slope of the volcano was bulging and it was collapsing. And this released the pressure in the system, creating a big eruption, a big explosive eruption. So let's just look at this here. So here you see the sliding of the bulging flank, and this gives rise or gave rise to this big eruption. And this has dramatically reduced the pressure in the system. It's like an uncorking of an eruption. And within a few hours, within a day, effectively, the ash had traveled for hundreds of kilometers all the way into the interior of the USA. And well, it caused a lot of local devastation, of course, as well. So Indonesia, another example, the land of 129 active volcanoes. It's the home to several very, well, infamous volcanoes. There's Krakatoa, there's Toba, there is Merapi, and there's, of course, the big eruption of 1815 and Tambora, and the year without a summer, 1816. All of this is going back to Indonesia. And let me quickly show you where these rocks would fall. They would fall also in the subalkaline part of the diagram here on the task. But there is a difference. This diagram is not very good at distinguishing subalkaline rocks from different settings. But in the calc-alkaline systems at subduction zones, we usually have lower iron but higher volatile contents. And that yields to a typical kind of assemblage. So let's talk a little bit about within plate magmatism. Magma is also generated within plates, and there, if it's in continental plates, we get flood basals, if or ring chains, and when it's In oceanic systems, it's more like island chains, like the Hawaiian island chain, for example. And if you take the Hawaiian kind of edifice, the big island Hawaii, it's 8 kilometers tall from the ocean floor. So it's a big volcano. If you spread that out thinly over a few hundred, kind of with a few hundred meters thickness, you get a large lava field, actually of the size of the Deccan Traps or other systems. So these are surprisingly similar. It's just that they're erupting in different systems. And the consequence is that you get the kind of situations like that, like on Hawaii, where you have lava flowing into people's gardens because, well, we have not fully understood some of these systems and we have gone a little bit too close. But the good thing is that with the goddess of volcanoes, Pele, you have probably heard you can calm her down by throwing gin into the crater. I hope it works, but I'm not entirely sure yet. The good news is that Hawaii is actually not an explosive system, generally speaking, and therefore, while property that is immovable will often suffer, people don't have to die in these eruptions, generally speaking. And here's the idea. We have this hot spot or plume, this melt anomaly in the mantle. We often assume it to be stationary and the plate is moving. The Pacific plate is moving very fast with about 7 centimeters a year, and that is making a very nice strung out chain. The Atlantic plate is moving less rapidly, only about 2 centimeters a year. And that means the islands like the Canaries or the Cape Verdes, they're more clustery. They are not as strung out and they're not forming these beautiful chains simply because the plate speed of movement makes a big difference here. So within plate, here we have a whole series of plumes, and this is probably the most famous one, the Hawaiian and Emperor chain. Often people ask what happens to these kind of chains, and here's the answer. Eventually, the the volcanic edifices, they sink below sea level, they get eroded down once they move away from the heat source, and eventually they will be subducted and they end up in a subduction zone. And here we have the Canaries, for example. There is no subduction on this end, but the plate on which it sits is pretty old, and sooner or later there may well be subduction in that area as well. So there's this funny kind of kink here in the system, and it's believed that the plate was starting to actually take a different direction at this point in time. I think this was some 40 million years ago, and there we therefore have a kink in that chain. There's a few more chains down here, and for the younger part of the Earth history, they seem to be aligned with the one on Hawaii, and that implies that we have a clear kind of direction of movement in the plate. So this is then an example from the Canaries here. This is a beautiful lava flow on the island of El Hierro. And there in the Canaries, it does resemble a chain, but it's not as nicely strung out. And here we have the oldest islands here in the western part and the youngest here in the eastern part and the youngest here in the western part. And the plate is actually rotating slightly, and there's the Madeira trend. There's a parallel trend, so that makes it rather convincing. And there we have a rotation of the plate, of the African plate into Europe. And the prime volcano there is the Teide volcano on Tenerife. And this is the strongest, but most of the volcanic eruptions are indeed in the western end of the archipelago. And we just had a big eruption in 2021 on La Palma. We had a submarine one in El Hierro, while eruptions here in this part of the archipelago are far less frequent. So here, just a picture of Tenerife. There's rift zones here, triple armed rift zones, and there's Teide volcano in the center of the island. Here's a beautiful little impression of it and a long-lived volcanic system. And this is, as I said, in part because we have different plate speeds as opposed to the Pacific. So just a few more beautiful impressions here. This is Teide, and Theta is usually very alkaline, I maybe should say that. It's more phonolytic, and that is typical for these ocean islands that are more evolved. We don't have a lot of phonolites on Hawaii because their magma flux is so rapid. But here in these systems where magma flux is a little less and the plate movement is also a little less, we don't cut the lavas or the magma systems off from the source. We continue to supply them, and that means we can differentiate more. So these phonolytic systems like Teide are typical expression of mature ocean islands with a more alkaline nature. So within plate magmatism, well, we have also flood basalts, as I mentioned, and here's an impression of the Giant's Causeway in Ireland, in Northern Ireland, sorry, but you get similar exposures also in Iceland, actually. And here we have large lava fields that come also from plume type volcanism. And we have plumes probably also in many parts of Europe. Here is a recent interpretation of the Central European volcanic fields. And there could be small plumes or plume fingers, as some people want to call them, feeding this very typically more alkaline magmatism, very small degrees of partial melting. It's very unusual anomalies. It's a bit like the hot piping in your pot of soup that comes up, and that can deliver some magmatism, of course. So in Hawaii, the Canaries, Iceland, etc., flood basalts, that's where we find our alkaline series. This is usually um, the initial stage. There can be subalkaline tholeiitic series, but often it goes from alkaline in these systems to subalkaline and then again to alkaline, low degrees of partial melting, going at maximum extent to somewhat high degrees, but then usually back to very alkaline nature. So when we look at the diagram here, we would be working in this part of the system. We are more alkaline because we've moved up here, and we get development up to phonolite. When we look at a last tectonic setting, it's the continental rifts, and we have them, for example, in the East African rift or the Rhone or Rhine rift. That's where we get super alkaline, and there we have a very low degree of partial melting. This is in incipient rifts. These are forming rifts, if you will. Many of them will not make it to become a real ocean. The Rhine Rift is likely going to be, well, aborted. The African Rift has started to be influxed by water, so maybe that will be one where Africa will break apart into two parts and a new ocean forms. But there, where we have a lot of volcanicity in those rifts, we also get a lot more evolved things, and that is often with crustal materials added. But in the low volcanicity rift, we have a lot of basalt, and it's usually very alkaline basalt. So there we either can have active rifting or passive rifting. In either case, we're getting these alignments of volcanoes. This is in France. This is the Chaîne de Puy. Here we have various volcanic cones, and here's the graben system. This is the rift system. The volcanoes sit on the flanks. Here's the volcanic chain. Here is the graben. To the right, the light colors here, the yellow colors are sediment. And here we have a lot of the volcanoes. Some lava flows were spilling into the rift valley, but most of the activity is actually on the rift flanks. Beautiful scenery there, it looks like here, and that is really alkaline. This is a phonolite dome, for example, the Puy de Dome, and the city of Claremore sits just somewhere down there. And this is in the task diagram out here. Some ocean islands will do that as well. As I said, Teide is phonolytic, so these two alkali series, they are really ocean islands and initial continental rifts, while most of the volcanism is actually here in the subalkaline area. And the variations are really here on this end in the source, and the variations that go to the site is usually fractionation and differentiation. So this is a decrease of partial melting in the source, while this is evolution of magma, bringing it to the right. So then we can close here with the 5 magma series as a summary. The tholeiitic to rhyolitic is about 84%. So this is the most dominant source of volcanic rock in the world, and usually it doesn't reach up to rhyolite. It's usually basaltic, and this is mid-ocean ridges and sometimes at ocean islands. Then calc alkaline to rhyolite is about 12%. That is usually in subduction zones. Alkali olivine basalt, it's in plumes in ocean islands. It makes only about less than 4%. And the ultra alkaline systems that we see in plumes and continental rifts, they make less than 0.5% of all the volcanic rocks. So here we have these main systems here. We have hotspots, plumes, and we have subduction zone. But the most prolific source of volcanism is actually here at mid-ocean ridges. And with that, I say thank you very much for your attention, and I hope you found that useful. So thanks. And I will link the other lecture, the other introduction lecture in the little box below. So hopefully you have a chance to have a look at that as well. Thanks a million and all the very best.